Now there should be some recording going on. Excellent. All right, welcome to Math341, Lecture 2. If you're still trying to decide if this is the right class for you, email me. Happy to chat with you about whether or not this is a good fit. What I want to do today is I want to talk about some of the most important sequences you will see in math, the geometric series formula, and how we can use this to start to model various processes. Now, the more involved your model is, the more likely it is to be applicable to the real world. The also corollary to that is the more likely it will be that you can't do anything with it. So you need to balance the two. You want to capture as many features as you can without making the model so complex that it is not plausible. So what we will do today is we will start off with a very implausible model. So I'm going to consider a game of hoops. These two people are alternating shooting. First one to get a basket wins. Who can name for cultural extra credit the two people? Yes? Magic Johnson and Larry Bird. Larry Bird. All right. How many of you are familiar with the McDonald's commercials, Nothing But Net, between Bird and Jordan? Or the movie Space Jam? But I grew up in the Larry Bird, Magic Johnson era, so I will stick with these two players. All right. So Bird and Magic alternate shooting. First basket wins. Bird always gets a basket with probability P. Magic always gets a basket with probability Q. Sometimes you use Q to denote 1 minus P. Another way to do this is instead of using P for Bird, I could do P sub B to remind myself that it's the probability of Bird getting a basket, and then P sub M for the probability that Magic gets a basket. You want to think what notation is going to be the best for you. And I want to let X be the probability that Bird wins, so I want to calculate what X is. Right? How many of you have taken econ classes? Okay, good. So you are used to unreasonable assumptions that have absolutely no bearing on the real world. Wonderful. For those of you who haven't, this is your introduction. So I am going to make several unreasonable assumptions. I will assume Bird and Magic never tire. They don't need, well, they can even take a bathroom break, but they never tire, they keep shooting, and their probability of getting a basket never changes. And they will keep shooting until the game ends. Okay? So we want to calculate the probability that Bird wins. What's the probability that Bird wins on his first shot? P. So, okay, what's the probability Bird wins on his second shot? 1 minus P, 1 minus Q, times P. So Bird has to miss, Magic has to miss, and then Bird gets it. All right. Well, once we figure out the probability that Bird wins on his second shot, miss, miss, hit, then the third shot and etc. is going to be very similar. Miss, 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 hit. And in general, for Bird to win on the nth shot, this has to go on n times. Whenever you see an expression that is repeated multiple times, this is a strong indication that you might want to introduce a symbol for that. So let's let R be 1 minus P times 1 minus Q. It's the probability that they both miss. And then we get X, the probability that Bird wins, is just P plus RP plus R squared P plus R cubed P, etc., etc., etc. So this is the geometric series. How many of you have not seen the geometric series before? Okay, my first year at Williams, I was teaching differential equations in the spring. Linear algebra is not a prereq for differential equations. But I felt it would be wrong to teach differential equations without talking about systems of linear equations, because you need that to do good modeling. So I wanted to just use 2 by 2 matrices, and I asked the class, how many of you would like a review of 2 by 2 matrices? Silence. Does anybody want to see a review? Nothing. And then I had clickers that day, and I said, okay, I'm not going to report on the results to the class, but press 1 if you want to see a review of 2 by 2 matrices, and press 2 if you don't. I never said I wouldn't report on the results to other classes. I just said I wouldn't report on the results to that class. 43% wanted a review of 2 by 2 matrices. And not one person was willing to say, I'd like a review of 2 by 2 matrices. So if there is ever something that you would like to see, please speak up. People nearby go, oh my God, we're going to do that. Well, inside they're going, thank you for asking that. So please, don't be afraid to ask or say, I'd like a review of that. All right, so this is the geometric series formula. I can factor out the P. It's 1 plus R squared plus R cubed. We know how to prove the geometric series formula. Normally, I actually bring the basketball hoop to class for this. If people want, I will bring it in the future. The problem is that I'm running back and forth between 2 classrooms, so I don't have as much time to set things up. I'm going to prove the geometric series formula for you by playing a game of basketball. Right? So does everybody agree that this is the answer for the probability that Bird wins? One of the great insights in mathematics is to take a hard problem and look at it a different way. And if you can calculate something two different ways and they're equal, then you often get beautiful formulas. So we're going to calculate the probability that Bird wins a second way. So let's do it without the geometric series formula. And in fact, this will allow us to prove the geometric series formula. So let's go back to X, the probability that Bird wins. So Bird could win on his first basket. Imagine Bird misses his first basket. From this point onward, what is the probability that Bird wins? All right, let's make it a little bit easier. Let's say Bird misses and Magic misses. So they both miss. Yes?
Isn't it the same?
The same as what?
As the first, before the first shot.
Right, so what would that be?
If they both miss, then it goes right back.
It goes right back. So what would be the probability that Bird wins after they both miss?
P, plus, the same.
So what is the same? You have to tell me. What letter?
P.
No, P is the probability that, you are so close. P is the probability that Bird makes the basket.
Okay.
I want to know the probability that Bird wins.
P plus PR.
Okay, you did this whole long expression.
Yeah.
Right. There's a simpler thing you can say rather than that whole expression. X. Just X. Oh. Right? X is the probability that Bird wins. Once they both miss, then from this point onward, it's like we reset the game. It's a memoryless process. It doesn't matter how we got there. So there are a lot of games where it doesn't matter the moves that brought you to that point. All that matters is the configuration. Any chess enthusiasts here? Does it matter how you get to a configuration on a chessboard?
Almost never.
Almost never is the correct answer. You can't have a repeat of position 3 times in a chess game where it's automatically a draw. Most of the time, though, you're not going to have repeat. For the most part, it doesn't really matter how you got there. It just matters what you're there. But you have to be careful. So from this point onward, it's just X. Well, now we can solve for X with some algebra. We're calling 1 minus P, 1 minus Q, R. So I get 1 minus R times X is P, or X is Q over 1 minus R. But we also know that X is P times the geometric series. So now we can cancel the P's, and we're done. What do I need to assume about P to cancel? This is a math class or a stats class. It's not 0. So as long as the probability is not 0, we can cancel. All right. And then that will give us a formula for the geometric series. Now let's think about the formula for the geometric series. What is normally true when you want to apply the geometric series formula? What do you have to assume about R? Yes?
Smaller than 1.
Smaller than 1. Almost, but not quite. You have to phrase it a little bit carefully. Yes?
Smaller than 1 but not equal to 0?
Nope.
Has to be smaller than 1, bigger than negative 1.
Smaller than 1, bigger, or the absolute value has to be less than 1. Negative 2018, you have to be careful. Negative 2018 is smaller than 1. So we need the absolute value of R to be less than 1. Typically, we only do this for real values, but if you go higher in mathematics and statistics, you'll have exponentials and Fourier series, and you might want to use complex valued numbers as well. For this, we'll keep it real. What values of R am I allowed to take for this? So R is equal to 1 minus P, 1 minus Q, and P and Q are probabilities. What can you tell me about probabilities? Yes.
They're going to be positive and less than 1.
Not quite positive. You got to be a little bit better than positive.
They're going to be non-zero and non-negative and less than 1.
Well, I'll agree with the non-negative. They could be 0.
Right.
There are certain things that will not happen, and they will have probability 0. And there are some things that will absolutely happen, and they will have probability 1. But you are never going to have a negative probability. So could 1 minus P, 1 minus Q, could that ever be negative? No. So in this formula, I'm not proving the geometric series formula for all values of R less than 1 in absolute value. I need R to be of the form 1 minus P, 1 minus Q, where P and Q are probabilities. Could I take P or Q to be 1? Yeah, that just means bird or magic is damn good, and they don't miss. So I can absolutely have I equals 0. Could I have P and Q both be 0?
That would be unrealistic.
It would be unrealistic. So bird and magic are playing. Each one has 0% chance of getting a basket. What's the probability bird is the first one to make a basket? 0%. The answer, it doesn't make sense in this case. And so you always want to look back at the formula and say, well, what would happen if I actually tried to put in P equals Q equals 0? What happens in extreme cases like that? So I can get any number between 0 and strictly less than 1. As a nice exercise, if you know that this is true when R is positive, there's a trick you could do to take the geometric series when R is positive and get the result when the geometric series is negative. I'll leave that as an extra credit assignment. If you can figure out how to do that, shoot me an email. Don't include that with the regular homework. For those of you who've taken complex analysis with me, you can do this with analytic continuation. All right, so this is the hoops problem. What I want you to learn from this is the power of perspective. If you look at things the right way, it's often much easier. I will show you another example of this with a Rubik's Cube later. This is Rosh Hashanah. I am going back and forth between services and teaching today. There is a reason I am wearing this tie right now. I know 2 of you in the class know the reason. If you look at the tie the right way, there's a message in it. Yes, putting your head like that is a good idea. I will also try very hard to remember to take this off before I go back to services. A lot of times things are hidden, and they are staring you right in the face. If you can look at them the right way, they become trivial. So much of mathematics is pattern recognition. And that's what I really want to try to emphasize in this course. How do you look at things the right way? All right. We can often circumvent algebra with a deeper understanding of what's going on. The fact that we have a memoryless process here is absolutely wonderful. The depth of a problem is not always what you would expect. We broke this up as an infinite sum. And this is an idea we're going to see again and again in the semester. If we have a complicated process, let's break it down into a lot of smaller, simpler ones, understand each one of them, and then somehow combine them. Now, unfortunately, this leads to an infinite sum, and infinite sums in general are very hard. We've already talked about how Calc 2 is the class of lies. You cannot integrate, I cannot integrate. Most sums we cannot evaluate, but we can often approximate them very well. Ideally, you would love to have an answer that depends nicely on the parameters of the problem. If we go back to what we had a moment ago, if I tell you Bird's probability of getting a basket increases by 5%, we can see exactly what that does to his winning percentage. We know how it changes P, and we know how it changes R. It is wonderful when you have a formula like that. A lot of times, especially if you're doing things in economics, you have very complex models, and you have so many things going on, you don't have a closed form expression, so you have to resort to simulations to see how things will go. If you have an explicit formula and you can see how things depend on each other, absolutely wonderful. Very important to know more than just the minimum. There's a lot of stuff we can do here. All right. Any questions on what we've done so far? Okay. I'm going to turn this off now, or try to turn this off. Take 2. There you go. Okay. So, in what we were just doing, we had broken a complicated problem into a sum of simpler problems. And we calculated the probability for each one, and then we added them together. So there is a lot of different ways you can do probability, where you can try to come up with rigorous axioms of how do you proceed. And unfortunately, I see some of you smiling because you know the punchline, some of the axioms that you think are reasonable lead to very strange results. One of the most famous is the Banal paradox, where you can take a perfectly solid sphere, divide it into 5 disjoint pieces, rotate and translate the pieces. Now, if you rotate a piece, should you change its volume? If you translate a piece, should you change its volume? You can take these 5 pieces and assemble 3 of them and get a full sphere with no holes, and then assemble 2 other ones and get a full sphere with no holes. And you should basically be able to double your sphere. Instead of doing a sphere, you could do a stack of $100 bills. Right? Some of the axioms we want to put in have some very strange consequences. Fortunately, the sets that you have to divide into are such strange, complicated sets they can't physically be done. These are strange mathematical constructions where you look at choosing representatives of equivalence classes. And we'll probably talk a little bit more about this. For the most part, since this is a first course in probability, I'm not going to get into the deep, real analysis, set theoretic underlurkings. But I want you to be aware that it exists. And for the most part, we're going to stick to simple events and just assign probabilities to simple events. What's the probability I land in an interval? What's the probability I take on a specific value? We're going to be talking about something like that. We are not going to be trying to assign probabilities to any possible event. And that's when the trouble comes into play. As a general rule, whenever you have to deal with an infinity, things can become very dangerous. All right, so what we are going to need to do is a mixture of combinatorics and probability. How many of you have not seen binomial coefficients? So binomial coefficients, n c k, or n choose k, or n factorial over k factorial, n minus k factorial. This is the number of ways to choose k people from n when order does not matter. Okay? So think of it as you're choosing representatives for student council. All student councilors are equal. If order matters, then you're choosing the executive committee. The president is different than the vice president, is different than the secretary. Okay? Has everybody seen something like this before? Where n factorial is n times n minus 1, n minus 2, all the way down to 1. Can somebody tell me what does n factorial mean? Yes?
A number multiplied by all the numbers below it.
Right, so what's the interpretation of that? So this is the number of ways of choosing k people from n when order doesn't matter.
All the possible.
Yeah, all the possible ways to order n people.
Yeah.
So this is the number of ways to order n people. So n factorial over n minus k factorial, and here order matters. Because if somebody's placed first, that's different than placing them second. N factorial over n minus k factorial, this is just n minus 1, all the way down to n minus k minus 1. Okay? And this is the number of ways to choose k people from n when order matters. Well, if you have k people, there's k factorial ways to rearrange them. And that's where this dividing by k factorial comes from here. So is this in view with the camera? Okay, excellent. So this is the one part where I can't see it. Okay. So this is some of the basic combinatorial items. Let's go back and let's revisit the birthday problem. And so fortunately, we did have everybody come to class who was necessary so that we did have 2 of you having the repeated birthday. Okay, my streak is still alive. I want to analyze the birthday problem. And very similar to the basketball problem, I don't want to just get an answer by brute force. If that's the only way I can do things, I will do it by brute force. But if at all possible, I would love to have an answer with a parameter to see what will happen. So for instance, I will start off by assuming there are 365 days in the year. But eventually I want to replace 365 with some variable, either d or n, something like that. And so I want to calculate, how many people until, say, 50% chance that some share a birthday. So how many people do I need before I have at least a 365% chance that people share a birthday? One of the big ideas in probability is it's sometimes easier to calculate the probability that something doesn't happen. And if you know the probability that something doesn't happen, then you can calculate the probability that something does happen by doing what? 1 minus, right? So there's a 70% chance that it's going to rain. There's a 30% chance that it's not going to rain. Why is this easier? Well, if I want to look at, let's say I have 30 people. I could have multiple pairs of people having the same birthday. I could have triples. I could have a triple, a quadruple, and 5 doubles. There are so many different ways to have people sharing birthdays. But if nobody shares a birthday, that's great. That means all the birthdays are distinct. So let's let Pn equal probability n people have n distinct p days. And so what's nice is we just have to calculate what n would make this 50%, and then that will be that will also be the n that will give us a 50% chance that they have the same birthday. All right. Imagine we have just one person in the room. What is the probability all the birthdays are distinct? 100% 1. All right. We all agree that this is not that exciting. I do not like writing it as 1. How should I write it? I don't want to write it as 100%. I'm sorry, no. 365 over 365. That's getting closer. That's also a good way of writing 1. I'm sorry?
365 factorial or 265 factorial?
Almost.
365 choose 0?
Almost. 365 minus 0 over 365. Or another way, I'll leave it like that. Now I have my next person come into the room, and I want them to have a different birthday than the first person. What's the probability the next person, when they come in, has a different birthday?
Minus 1.
Yeah, then it's going to be 365 minus 1 over 365. And if we have n people, what do we go down to? No, almost.
N minus 1.
I know, this is where it gets so annoying. Is you have to remember that it goes all the way down to n minus 1, because we've started at 0. All right, so we can write this in a more compact notation. We're going to use product notation. It'll be the product, k goes from 0 to n minus 1, of 365 minus k over 365. Or another way of writing this is it's the product, k goes from 0 to n minus 1, of 1 minus k over 365. Right. It is not a prerequisite to take a class with me to take a class with me. If so, no one would ever be able to take one of my classes. But I know several of you have taken classes with me. And for those of you who have taken a class with me, you are on the hot seat now. What should you be thinking at this moment in time? Log. Whenever you see a product, you must have a Pavlovian response of taking a logarithm. The only exception is maybe if you're volunteering in an elementary school and teaching little kids how to multiply numbers. All right, so we want to multiply by 4 times 3. So we take the log of 4 and the log of 3, we add them, then we take the anti. Okay. That's a good place not to use logarithms. But otherwise, if you see logarithms, you should always be thinking, if you see products, you should always be thinking logarithms. Why should we be thinking logarithms when we see products?
Because sums are nice and products are hard.
Sums are nice, products, aha. Has anybody ever taken a class in advanced product theory? Has anybody ever done the Riemann product? No. We have done formulas for sums. So I am wearing a slide rule tie clip. It is actually a working slide rule. For those of you who prefer the more standard ones, these are great. And in old days, they would convert mathematics and do it like this, or engineering. For those of you who really want to go circular slide rules, far superior. I love the circular ones. These are outdated technologies. Right? You do not need to learn how to use a slide rule. It's not a bad skill to have. It's hard to find them these days for good reasons. The calculators you have now on your phone, the computing power is more powerful than the NASA space probes from the 70s. It's incredible how much technology you have available. But there are still some really good ideas of all of this. And the ideas behind all of this is convert multiplication to addition. We can do addition and then just convert backwards at the end. So for something like this, we want to convert this to a logarithm. So I'm going to try to keep the space concise. And so what we're going to do is we're going to look at the log of Pn is the sum, k goes from 0 to n minus 1 of the log of 1 minus k over 365. All right. So one of the prerequisites for this class is calculus. one of the big ideas in calculus is you take a complicated function and you replace it locally with a simple function. And the first thing you do is you do the tangent line approximation. And then if you want more detail, you might start to do a Taylor series expansion. We maybe find the best cubic or the best quadratic, best cubic, best quartic, and so on and so on and so on. But the idea is you take a very complicated function and you approximate it with a simpler one. And the idea is if you are pretty close to the expansion point and your function is not too wild, it should be a pretty good approximation. For a lot of things in life, we do not need to have the exact answer. Have I done the American Airlines example yet in this class? I'd imagine you own American Airlines. What is your goal? What's your goal?
Sell it.
It's actually not a bad goal. I've flown them a lot. And I don't mind that this is being recorded. All right. What is your goal if you own American Airlines? Make money. Your goal is not to fly people. How do you think you make money? Hopefully by flying people, right? But you want to figure out what's your optimal schedule. There's an incredible amount of probability and statistics that goes into trying to estimate what demand routes are. For those of you who are at Williams and have flown through Albany, Albany is not one of the major airports in the country. If they need to move a plane someplace else, we are high up on the list to have canceled flights. I've been in the airport and seen like 4 straight flights to Albany, all canceled. So there's a lot of good probability that goes on to try to estimate things like this. Okay? For a big airline like American, if you're trying to figure out your optimal schedule, you're talking in the tens to hundreds of millions of dollars. If you're within $50,000 of optimal, that's good enough. You don't have to find the best schedule. You just have to find a schedule that's pretty good. The other thing is, you're going to be using statistics to try to estimate parameters for your model, right? How perfectly do you think you can estimate these parameters? So if you insist upon an exact solution to your model, and your model is only an approximation to reality, do you really want to insist on the exact solution? So for a lot of things, just getting close is enough. So for a lot of problems, if I can just get close to my function with something that's simpler, I'm in great shape. So what it looks like we have here is we have the logarithm function. And the hope is that 365 is going to be much larger than k, so that this is very close to the log of 1. So what's the log of 1? 0. So let's look at the Taylor expansion of the log of 1 minus x. So f of 0 is just going to be the log of 1, which is just 0. F prime of x is 1 minus x, and the log of 1 minus x will be a negative 1. So f prime of 0 is going to just be negative 1. So f of x is approximately negative x if x is small. So this is the first order Taylor series. This is the tangent line approximation to the logarithm. If I wanted to do better, I could just keep the second term. Well, I can feed that in, and I get that this is approximately, and I go ballistic when people write inequality when it's no longer an equality. It's not quite as bad as writing Go Yankees, but it is close. Okay? So make sure you are clear. When is it an equality? When is it approximately an equality? So this is approximately the sum, k goes from 0 to n minus 1, of negative k over 365. Well, I can pull out the negative 1 over 365. I'll have negative 1 over 365. The sum, k goes from 0 to n minus 1 of k. All right, so now we just need to evaluate that sum. How many of you have never seen the sum of the first n integers, or n minus 1 integers? This is one of the standard go-to induction problems. All right, I will give you the Gauss proof. So you have 1 plus 2 plus m minus 1 plus m. Let's call that Sm. And to make you feel bad, Gauss did this when he was around 5 years old. His idea was to write the numbers backwards. M plus m minus 1 plus get twice SM. M plus 1, M plus 1, M plus 1, M plus 1. So I get M plus 1 a total of M times. So I get SM is just M plus 1 over 2. You can also prove this by induction, but it's nice to see this proof. You could also use this to prove the geometric series. This is the standard way the geometric series is proved. You'd have 1 plus r squared. Rather than writing things backwards, you would just multiply by r, subtract, and you have massive cancellation. So because of this, we can actually evaluate this sum. This is negative 1 over 365 n minus 1 times n over 2. Is that still in the range of the camera? Excellent. All right. So now, what do we want this to equal? What do we want this to equal to solve our problem? I'm sorry? I think I heard it from the back. What do we want it to equal? Log of 1/2. So we want the log of 1/2 to be approximately equal negative 1 over 2 times 365 times n minus 1 times n. The reason I'm not multiplying the 365 by 2 is at the end of the lecture I want to do a search and replace and I want to move to Pluto, where we'll have 90,000 days. So I want to keep it like that. Well, what's nice is the log of 1/2 is negative log 2. So we get n minus 1 times n is 2 times 365 times the log of 2. Okay? And you can yell at me for dropping the approximation. So just canceling the negative sign. How would we solve this? We have n minus 1 times n is approximately that. How would we solve that? Yeah?
Well, if you just want an approximation, just write it. It's approximately n squared, so you just take the square root.
So one thing is I could say it's approximately n squared. Let's just do that. If you didn't want to do that, what would you do? How would you solve it? So how would we solve this equation? If I wanted the exact answer.
Quadratic?
Yeah, quadratic formula. You know, ax squared plus bx plus c equals 0, so x is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. So we could do that. But then that would give me a much worse answer in terms of just looking at seeing how things depend. Instead of calling this n squared, so you are discriminating. You are weighing n more than the n minus 1. Somebody could say, well, why don't we call it n minus 1 squared? Or, what could we do instead? N minus 1/2. Call it n minus 1/2 squared. Because if you expand this out, you'll get n squared minus n plus 1/4. Oh, come on, we're differing by 1/4. That's not that bad. So that's going to be approximately 365 times the log of 4. And I'm just moving the 2 inside. So then I get n is approximately 1/2 plus the square root of 365 log of 4. Okay? And now if we wanted to change 365 to d, so if we have d days, we would get, we'll call it maybe n sub d, would be approximately 1/2 plus the square root of d log 4. And what's really nice about this is you can see how the answer depends on the number of days. You have an explicit dependence. It is wonderful when you're able to get something like that. You can also check and see how bad is the approximation. How close is this to the truth? And I will quickly punch up. Got Wolf alpha already punched up. So we wanted to do 0.5 plus the square root of 365 times the log of 4. Okay. And the answer to that, which should not take this long to calculate, it's still computing. All right, 22.994. $22.9, that's not bad. So it's worth going back and looking at problems like this and seeing what is difficult, what is not difficult. We want to arrange computations in a way to be practical. The technology you guys have is much better than the technology I had when I was a student. I was forced to learn how to use log tables and trig tables. The technology I had is better than the technology my parents had. The first time I taught probability, I was a postdoc at Brown, and I was coming there from Ohio State, and I tried to get a copy of the book before I arrived at Brown so I could start preparing my lectures. And I couldn't get a copy of the most recent edition. I got a copy of the second edition of the textbook. And it was, one problem was a simple combinatorial problem, and the answer is a nice factorial divided by another factorial. And the book says, at this point you would think you've solved the problem, but you haven't. I'm going, no, I've solved the problem now. It's just... And then the book goes on, now you have to compute the factorials. I go, oh, yeah, back then that would be very hard to do on the calculators people had for the second edition because the book was so old. Yes, okay. If you go back to trying to multiply, what did we have? We are multiplying numbers. So we had a product, k goes from 0 to n minus 1, of 365 minus k over 365. I could write that as 365 minus k factorial divided by 365 minus, I think, n factorial 365 to the n. And if you try to do this, you're going to get an overflow for various values of n. You can't just put an n. Now, what you could do is you could compute successive ratios. Let me first compute the 365 over 365. Then I'll multiply by 364 over 365. Then I'll multiply by 363 over 365. And I'll keep doing this until I get to the point where I get a half. But you've got to be very careful about round-off errors. Can you trust the results of your computer? How many of you have heard of the Pentium bug? My wife is a professor of marketing. This is one of the few things we both teach. So there's a beautiful thing in mathematics called prime numbers. I spend a lot of my life looking at them. And it turns out that occasionally primes differ by exactly 2. As the only even prime is 2, all the other primes are odd, so you can't really be closer than 1, except for the primes 2 and 3. And it was proven that the sum of the reciprocals of the twin primes converges. But people didn't have a really good estimate as to exactly what it converged to. It converges very slowly. And so Nicely was trying to calculate more digits than had been done before, and he's running it on his new computer, and the results he gets does not match with the previous results he got on his older computer. How many of you have heard of Intel? What does Intel make? Processors. And so they used to call their processors the 286, the 386, the 46. Then they launched a big marketing campaign that the most important part of the computer is the processor. That's what matters. And they called their new chip the Pentium chip. And the Pentium chip actually had trouble with division. It would occasionally give you the wrong number when you divide it. Now, Intel actually knew about this, but they figured, who's going to have to do 1 billion consecutive divisions of numbers this small? It's not worth mentioning the fact that there's an error in the chip. Well, when Nicely then discovers this, the competitors of Intel have a field day. We agree with Intel that the processor is the most important part of the computer. Ours can do division. And then you start having all these people who are frantic, who are requesting a new processor that can divide. If you are trying to launch a rocket ship to the moon, yes, you might have to worry about precision. Most people were not doing anything that required this level of precision. And most people were absolutely fine with it, but there was this panic. And it cost Intel, I believe, in the order of hundreds of millions of dollars. They knew it beforehand, but they figured, who's going to find this out? So this is one of the advantages of doing pure theoretical mathematics. Occasionally you can use this to check results. But you've got to be very careful. Can you trust your computers? Can you trust the output they're giving you? When it's a long process that has overflow errors, you have to be extremely careful. I believe one of your homework assignments is to calculate this ratio. And if you calculate this, you should see something very interesting. And if you want to see more interesting things than this, I think another interesting one would be 9998999. I think that one is also interesting. And there might be a pattern of which ones are interesting and why. And so in this class, I am going to require you to do some programming. I'm going to ease it in. I am happy to have an entire class that we'll have in the near future devoted to just programming. This does not mean that I expect you to be able to write code to get that rocket to the moon. But I want you to be able to do some basic simulations. I want you to be able to write some code to estimate what probabilities are. This means being able to do simple things like for loops, to do if statements. I do not care what language you use. I just want you to have this as a skill that you can write simple code to investigate stuff like this. When I was a postdoc at the American Institute of Mathematics one summer, somebody presented a really interesting math riddle. Take the numbers 1, 2, through 9. Use each number once and only once and form 3 fractions, where the numerators are 1 digit and the denominators are 2 digits. So maybe 2 over 98 plus 3 over 14 plus 7 over 56. If you choose the numbers correctly, you can get that fraction to add up to 1. And so the question was, how do you do this? So I am surrounded by some of the best number theorists in the world. And they start proving results about the digit 5 must be in the following, stuff like this. What do you think I do? So, yeah, I write a computer program. I don't even bother writing an efficient computer program. There's only 9 factorial ways of arranging the numbers. It's not worth spending any time to do a clever code. How many times does the program have to run? How many times do I have to run my program? Once. If you only have to run it once, is it worth spending time to make the program run efficiently? It's not worth spending 6 minutes to save 1 minute of runtime, right? What if you are putting this on your cell phone, and the cell phone is going to be used and doing this process thousands, millions of times? Then you want to be efficient. But if you're doing something, if it's once and done, you can afford to code inefficiently. So I didn't even bother doing anything efficiently. I just did the most inefficient code I could. Store all 9 factorial possible permutations, go through each one of them and check, and then spit out all the ones that work. Because I could write that code in half a minute, I think. It wasn't worth the time. All right, so I'm going to end on just one more thing on efficiency, and then starting on Wednesday, we'll really get into the probability stuff. Anybody know what our heritage is from the ancient Babylonians? What have they bequeathed to us? What are we stuck with from the Babylonians? Yeah, what number in particular do we get from the Babylonians? I'm sorry?
0.
Not 0.
10.
Not 10. 10 is a nice base, right? We all agree 10 is nice to work with. What base did the Babylonians like? Not 2. Babylonians like base 60. How many seconds are there in a minute? 60. How many minutes are there in an hour? 60. How many degrees are there in a circle? Oh, we love the Babylonians, right? We are stuck with numbers like this. We are not going to change. To get a sense of how we will not change, who can tell me what comes next? E. What comes next? R. T. Where does QWERTY come from? The keyboard. Does anybody know why we have keyboards with the letters like this?
It was like initially when it was designed for typewriters, it was so like you wouldn't have consecutive letters next to each other for jamming.
Yeah, because you'd be pinging things down, and so they were trying to get you to alternate using different hands so that you wouldn't have 2 things coming and getting jammed. The keyboard was designed to slow you down and be inefficient. Modern typists who do it professionally use the Dvorak keyboard or other things. Why do you think we still use QWERTY? Because we don't love you. We don't want to change. So we force you to learn the way we learned. And then you force your kids to learn the way you learned. And the cycle is never broken. So things get institutionalized. It is very hard to change something like this. This is why whenever you're introducing new notation, whenever you're doing a new problem, really think about how you want to define things. Really think about what quantity you want to study, what notation you want to use. Because things can get stuck. Okay, we are not leaving the QWERTY keyboard. We will have it for a long, long time. The Babylonians worked base 60. So how many multiplications do you need to know for base 10? You need to know about 100. Or if you use symmetry, you can do about half of that, about 50. So for the Babylonians, so you have base 60. So if you want to do x times y, how many multiplications do you need approximately? You need about how many? How many multiplications do you need to memorize? About a little bit better than 1,000. Yeah, I mean, there would be 3,600 if there weren't any repeats, so half of that is 1,800, but then there's some squares, so it's about 1,800. You are not going to memorize 1,800 multiplications. So the Babylonians came up with some very clever ways of multiplying. And again, this is going back to our talking about doing things efficiently. This is something they're doing over and over again. You can have tables. The lookup table is one of the great inventions in science and engineering. You can have all of this stuff codified, but the problem is you don't want to have to lug around that many stone tablets or clay tablets. So what the Babylonians noticed is the following. X times y is x plus y squared minus x minus y squared divided by 4. So rather than doing a multiplication, we're going to do 2 multiplications, a subtraction, and a division. And this is an improvement. The reason is this is just squaring. Subtraction is easy. Division by 4 is not that bad. Another way you could do it is you could do it as x plus y squared minus x squared minus y squared over 2. Either one would work. But the idea is to take a very complicated problem and break it up into a lot of simpler ones. So here, rather than doing a generic multiplication, we're now doing very special multiplications, just squaring. And now you only need a table of squares. That's on the order of maybe 60 or 120 items to store. Much better than 1,800. So I just wanted to talk a little bit about this as just some general philosophy for the class, for the mindset I want you to be in. I really want you always to be thinking, when you're doing something, is this a calculation we can do? Is it feasible in the amount of time we have? There are some simulations or some brute force approaches that will take too long to do. And so you have to find clever ways. If you look at the combinatorial expressions, these numbers grow so fast, it is astounding how many possibilities there are. And unless we can find efficient ways to search through the spaces, we're dead. So a lot of times you might want to find what is the winning solution. Well, you enumerate your space and you go through the space. You can't do that because we don't have time. Frequently, the other thing I want you to get from this is the idea of approximating, of not getting the exact answer, but getting too close to the answer in a reasonable amount of time. And then if you need further detail, refining it. All right, so this is a good place to stop for today.